Hi, this is lecture 11, and we're going to cover Intro to Design of Experiments, which is probably mostly slides 2 to 66 today. It's one of my favorite techniques. I think one of the most important techniques, and it's one of those things that every black belt should know and should be able to pull off. And every green belt, you know what? It'd be great if every green belt knew it and knew the basics of it, and maybe you could even pull off simpler experiments. In any event, what's really powerful about it and really cool is that it's very different from what we've learned before. The techniques so far that we've learned and that we've covered in class and that pervade our all around society for the most part are looking backward techniques. Regression is an excellent example. Super powerful, but regression relies on historical data to be able to come up with a model. What we'll find is that DOE doesn't do that. DOE is very proactive, and so what it envisions is that you actually adjust your process based on certain factors, and you make very precise and very well-coordinated adjustments, and in doing so, you're able to see what happens to your output as you jiggle the inputs. But you do it in a controlled fashion. What it does is it allows you to understand exactly how those inputs affect the outputs and establish true cause and effect and quantify very clearly how much of that effect is there. Super powerful, allows you to really screen out a lot of factors that don't matter, allows you to optimize your process. It's one of the most powerful optimization techniques. And think about this too. What it also allows you to do is it allows you to test multiple things at once. Have you ever run a project or been on a project where somebody says, hey, let's try out all these solutions. Maybe there's 5 or 6 of them, and you just try them out. Trial and error. Let's see how they work. Maybe we try them one at a time. That takes forever, so we often don't do that. What we do is we usually just implement them all at once. How do we know which ones worked? How do we know which ones maybe interacted with each other? Maybe solution A interacted in a negative way with solution B, but in a synergistic way with solution C. How do we know? Well, in DOE, you can know. You can know exactly how much amounts, which ones were positive, which ones were negative, and which ones interacted with each other. Way cool. So let's dive into it and just kind of talk you through it. So there it is, Introduction to Design Experiments. Now, I just want to let you know that what we're doing in this is really introducing you to it. I want you to get when a DOE might be helpful. Notice might, okay? Doesn't mean you always have to do a DOE. I want to emphasize that. Not all black belt projects have a DOE in them. Okay, that's number one. Number two, you can, I would like you to be able to create, execute, and analyze what are called 2 to the k factorial DOEs. DOE is a broad subject. 2 to the k is, it's great on 2 reasons. Number one, it's the easiest to understand, although it's still, you'll get it for sure. I know you can do it. But there's a lot of notation that we have to get through. At the bottom of it, it's all just +1 or -1. That's it at the bottom of 2 to the k DOEs. So that's the number one, is they're fairly easy to understand, fairly easy to analyze, and happy benefit. They're awesome. They really work really well. And even after I've studied all sorts of other types of designs, cyclic designs, optimal designs, computer-aided designs, all kind of stuff, response surfaces to Gucci designs, I mostly go back to 2 to the k because I understand them best and because they've worked really well. So that's the good news. Now, let's talk about a little bit about that yellow box. If this is your first exposure, just keep in mind DOE is a big subject. Rome wasn't built in a day. We're going to cover the basics and hopefully you get them down pat. Number two, if you do decide to try a DOE, and I hope that you do, please consult with somebody who's done it before. Don't try it alone the very first time. You can contact me, which would be fantastic, mzabel@straightlineps.com. Love to hear from you when you're doing it. I'm happy to help you. But there's other people who have done it too. consult your local statistician, or what have you. Okay, and finally, don't think that DOE is just for statisticians, please. I mean, it is really at the heart of efficient scientific inquiry. That's what got us where we are today. Although we don't like to always say it, it is really science that has propelled us forward. Business can honestly use a little more science. Okay, so let's move forward. First of all, where would you use a DOE? Well, if you're in the classic DMAIC framework, there's a few different areas, and I'm going to highlight a couple others because here are the two classic areas where you'd use a DOE. To analyze the data, let's see if I can use my highlighter. Oh, come on. There we go. To analyze the data right here and to generate potential solutions. So in analyzing the data, sometimes a DOE can help you separate out things, and particularly in generating solutions and evaluating those solutions, you can use a DOE to help evaluate. However, the framework and the understanding of DOE is also very, very helpful. It can be when you're collecting baseline data and taking an initial look at the data. So the concepts of DOE can be very helpful there. Okay, now, to let you know, examples in this section are going to be done in Minitab. There's a free utility that I've written, and it's buyer beware because you get it for free, called DOE Helper, which does a few things. Okay, use it at your own discretion. I'll have a small video detailing how to use that for DOE. It's a little bit clunky. I'm not going to make any apologies for it. Just note that it is a little bit clunky. Excel statistics did not do it. We're going to do our work in Minitab throughout this section. All right, so here's what we're going to cover. We're going to cover what is DOE, why are we going to use it, a little bit of terminology, and then we'll take you through two very important concepts. The one is what's called the full factorial, and the second, which is the real star of the show, is called the fractional factorial, and that's what we're going to cover. But before we do, I want to do an example. So let's get to it. We're going to do an example from the financial industry. You may have heard that design of experiments is just for manufacturing. Not so. We're going to do one from the financial industry. Now, in this example that we're going to do from the financial industry, it's found in the data file I just had open right there. MKT. It's called DOE MKT_data.xls, and I'll show you what it looks like in just a moment. However, in this example, this happens to be from the financial services industry. What we can imagine is we have a DMAIC team, a Lean Six Sigma team, that was working on increasing their in good order on their applications. Now, what does that mean? Well, in good order simply means we're going to be looking at the percent complete. So imagine this. Imagine you're applying for, I don't know, a loan or a long-term disability or insurance or maybe life insurance, whole life or term life or whatever, right? Okay. They send you an application, you fill it out, and it's either complete or it's not. It's not complete if they can't continue that transaction. You can imagine that's a big problem for this particular company, right? Whether it's New York Life or MetLife or a Mass Mutual company or Fidelity or whatever, that's a big problem for them because it's a big problem on two counts. One is they have to send it back in order to really process that application, go back to the customer, and the customer is unhappy with it. So it costs them money, and the customer is going to be unhappy because it's going to take them more time, and they're going to have to come back. All right. So this particular team went through D, M, and A, and they were in the I phase. And they said, you know what, up until now we've really studied this, and we've boiled it down to three types of problems or things that really drive this in good order. And one is the application type, at least for the scope of their project. One is the application type, whether it's a loan or a lease or something like that. That's one of the things that really drives it. The second is whether or not we have examples in there. And the third is the amount of instructional detail that's in there. Now, you might think that those are three broad categories, and in fact they are. However, what this company decided to do was to go ahead and they brainstormed what are solutions that we can maybe try based around that and test those. So here's what they came up with. They came up with 6 factors, A, B, C, D, E, F, and G, and I'm going to label them that way, A, B, C, D, E, F, and G, that were driving the percent complete. Okay, they found 6 of them, and they decided that those 6 factors then would be A was the app type, application type. B was the region. C was the description. I'll get to what these are specifically. D was example. And E was negative example. So essentially they came up with basically 3 solutions. One is let's look at and change the description, not decryption, description. That's a little better. Let's provide an example in here, and maybe let's provide a negative example in there. Now there's a couple of different things that came up in that, and that was that in the discussion of the experiment, people said, well, maybe it really depends on the application type. Like maybe for one application we need an example, but we don't need a negative example. But for a different type, we need both. Or maybe for one application type, we need a long description, and for a different one, we don't. Also, that may vary by region, maybe northwest versus northeast or whatever. So in any way, they set up, for each one of these factors, what they did was they set up 2 levels. We'll call the level high, low, and we'll assign a -1 to that, and we'll call the high +1. Okay. Now, it wasn't completely arbitrary, but we can talk about what these different things were. So in this case, the low was loan, and the high was lease. Okay. For region, low was Midwest, and I don't want anybody to take offense at this. I'm a Midwesterner myself, so I've had to live under that yoke of supercilious coasts. Northeast and not northwest. Okay. However, this is just arbitrarily essentially assigned to -1 and +1. Obviously, this one we could switch around. Same with this one. Description, either the current, use current description, or we'll enhance it. So they're testing out their solution. In the example, we either use a current example, or we'll use the enhanced. Now, you might think that there was another thing that they could have written here. They could have had it as 0 or 1. Don't use any example at all. Use one, etc. We could have had another factor, but they just used 5. And finally, negative example, none versus yes. Okay, so these are the -1s and these are the +1s. Now we could have written them that way. We could have written them that way as -1 +1, -1 +1, -1 +1, and there would be advantages to that. But let's just leave it at this for now. So here was the experiment that they had. Okay, so I want you to note that they had 5 variables. Each one has 2 levels. So that would be 2 to the 5th. If we wanted to run an experiment with each combination, it would be 2 times 2 times 2 times 2 times 2 combinations, which is equal to 32. That would be a full factorial. Speaking some of the language here, full factorial. But instead, we are going to use 16, which is 2 to the 5 minus 1. And yes, I'm writing it that way, not 2 to the 4, because we have 5 of these guys, but I'm running a half fraction. This is called a fractional or a half fraction factorial. Okay, so in fact, in the experiment we're going to look at, we ran this guy. Okay? All right, at this point, they set up the design. They set up the design. So let's go to it and let's take a look at it. Here's the data. When they started out, it would have looked somewhat like this. I'm going to hide this. It would have looked like this. This was their experiment. So you'll notice there's different combinations that they're looking for. How did they choose those? Well, we'll cover. We're going to actually let Minitab do it, but at the moment, this is what it is. Okay. I'll unhide. And what I'm going to do is I'm just going to copy this over to Minitab. You know what yes, I'm going to copy the whole thing over. Now just keep in mind that when they started the experiment, I'm not going to worry about the standard deviation here for a moment. When they started the experiment, they wouldn't have had these percent completes. But think about it this way. You know what? I'm just going to get this into Minitab when we talk about it there. Okay. So when they started the experiment, they would not have had C7. C7 is what's generated after they would send out all the applications that had these combinations. So maybe they had a certain, I don't know, maybe 100 of them that they said, okay, let's send 100 that are loan applications. We're going to send it to the Midwest. We're going to use the current descriptions, current example, and yes, we're going to use a negative example. And then we're going to send 100 more that are lease applications to the Midwest. We're going to use the current example, current description, current example, and no negative example. That's almost like baseline, right? And then we're going to have 100 more. We're going to send out 100 loan applications to the Northeast using current, and no negative example, and so forth, okay? When they did all that, they got a response back, and they looked at the percent complete, okay? Hopefully that makes sense in your brain to what was happening. Okay, so let's go through and now they've set up their variables, they've run their experiment, they've set up their experiment, they've run the experiment, and they got the results. Let's take a look at how they would have analyzed their results. Okay, so in this case we've got things that vary by all these different things. How can we possibly separate out what matters from what doesn't to find the key things that are affecting us? Let's go to it. So in Minitab, probably the easiest way is to go to Stat, DOE, Factorial. Now we've already created the design, so we are going to analyze a factorial design. Now in Minitab, if you've never done this before, Minitab comes up with a dialog box that says, whoa, I don't find a Minitab design in here. Do you have some data that you want me to help you with? Click yes. If you read it, that's essentially what it says. And it's going to go through and ask you for what are the factors. So more language. So the factors are the inputs. So factors would be app type, region, description, example, and negative example. Okay, I'm going to make a little instructive mistake. I'm going to click OK, and Minitab's going to get mad at me. Oops, I have to specify the low and high for each of them. I click OK. Now, normally I could type in -1s and +1s, and that would work just fine. Minitab will usually come up with those, but in this case I actually have to type what's there. So application type, the low would be Midwest, and the high would be, whoops, no, I'm sorry, low would be, I believe it was loan. High would be lease. Region would be, low would be Midwest. High would be Northeast. Description, low would be current. High would be enhanced. I want to spell it correctly. I want to use the same spelling that's in the file. Example would be, whoops, hey, come on now. Example would be current. High would be enhanced. And negative example, none and yes. Change that one there, not none. None. There we go. And click Okie dokie. And now we're ready to rumble. Okay, so when I click OK, Minitab's going to ask me, okay, now what response do we have? Well, the response that we have is the % complete. All right, now we'll talk a little bit about these things in just a minute, but for now I want you to go ahead and click on Graphs. Okay, now if you've been following, I like to be a little bit more aggressive with the factors that I find that are significant when I do a DOE. So I want to look extra hard. Generally speaking, I want to look extra hard for things that are significant. So I'll put this on a 0.10. You can leave it as 0.5 in the significance level. But just for the start, we are going to. I don't care so much about the significance level as I do just kind of looking at these plots. So we're going to do the normal and the Pareto. Most people. Their first thing they like is the Pareto. I personally like the normal half plot, or the normal plot. You'll see what it is. Both of them tell you basically the same thing, but let's take a look. Okay, so this is it. Minitab actually has gone through and analyzed for you. I'm going to show you both of them, and analyze for you all the significant factors and determine how significant they are. So it's actually built the model, and so what we're doing. Let's take a look at the normal first. We'll do this one time, and then you'll see you can use whatever one you want. Okay. So there's a couple of different things I want you to notice about this. Nothing earth-shattering on this, but I want you to notice a couple of things. First of all, there's all these dots over here. Now, the idea is on the normal plot is the stuff that's on the line is basically just like noise. It's just normal noise. It adds normal small variation to it. It's basically like common cause variation. However, the things that stick out, in this case C and especially D is the biggest effect here, are the things that make a difference in the design. So what this is saying is that the two key drivers are the description and whether there's an example. Whether there's a negative example doesn't make a difference. In fact, we can't even tell which one it is here. Okay? So that's it. Now, I want you to notice one other thing here, and that is lengths PSE. Now, what the heck is that? Well, what that is it's like a p-value. It isn't a p-value, but it's like it. Okay. Okay, we're just hanging in there, but it's like a p-value, and I'll show you why I say it's like in just a moment. Okay, here we are back in Minitab. Everything's going great guns. So I'm going to close down the half normal now. And let's take a look at the Pareto. Pareto tells me the same thing. There's my lengths PSE. Why is it 2 times that? I don't know, but it is anyway. Basically, we look at the things that are above the red line. Okay, again, we have that same lengths PSE, significance, all that kind of good stuff. All right, so what we can tell is that we've analyzed the data for a number of different things. Now, let me see now what the, so this says essentially that those two guys are big hitters, and all the rest of the effects, including the interaction effects. You see these AB, AC, AD, those are interactions. That's an interaction between AD is the significance level of the application type interacting with example. Very interesting. So it says that that's not significant, but if it were significant, we could find that out. Okay, pretty cool, huh? All right, let's utilize our Control E. But before we do, I want to show you a couple of different things. Here's Minitab's output in the session window. And in the session window, whoops, did I do it twice or once? Okay, so here's Minitab's output in the session window, and it says totally confounded terms. We'll talk about confounding a little bit later today in this lecture. But here are the confounded terms, and like I said, we'll get to that example. It looks kind of complicated to me. And here are the terms. So the Minitabs model that it built, and hold on to your hats, folks. Minitab built a big bad model. It built y is equal to constant, which is 73.15, plus some factor for app type. I'm going to call app type A. I'll say 2.375A plus did one for B. I'm not going to write out this whole thing because it would take forever. B plus something times C plus something times D. But it also built stuff for interactions. Okay. So far, okay. Now let's go down a little bit farther and let's see which terms are significant. Now we know we look at the p-value to do that. Oh, we don't have a p-value. See how we don't have a p-value? Now, we don't, and either that's a bummer or whatever, but that's one of the reasons why I said, oh, you look at lengths PSE, it's like a p-value. And it is like a p-value. It helps you understand what's significant or not. What we're going to do is we're going to figure out how to chop off the terms so that we will get p-values, and we'll get a more manageable model here. So it's no great shakes. It's no surprise here, and it should be relatively intuitive that what we're going to do is we're going to keep the big numbers here. So if I just circle those, they're going to coincide. My guess is that they're going to coincide. There's one right there. There's 8. You know what? Maybe I'll highlight instead. Now let me highlight these instead. Use yellow. Yellow seems to be a good highlighter color, right? So there's washed out. Great. There's one. There's one right there. There's another one. Those are pretty big, and then there's some others that are much smaller, but kind of on the next order of magnitude. So 2.6. There's a 2.4, a 2.4, and so forth. Yeah, and we'll find out that that's exactly the order that we're looking at when we looked at the Pareto. The first would be example. Guess what? That's D. The second would be description. Guess what? That's C. And then there was this AD interaction, right? Oh, let's see. App type times description. App type is A. Description is C. Oh, that's AC. I'm sorry. There's my AD. App type times example. That's AD. Okay. So all we're really going to be doing is taking out the terms that are insignificant and saying, you know what, those are really noise. Let's take them out of our model. So let's go ahead and do that. And I'll show you how to do that. To do that, we do a Control-E. Okay, and I'm just going to remind us by looking at the graphs. This time I'm just going to look at the Pareto. Okay, so here is our prescribed way of doing it. We're going to eliminate some of the things that are on the lower end, and we're going to look at the significance level change. So I'm going to remove everything but the main effects and some of the big interactions. Okay, so let's go with, let's see, I'm going to keep all the main effects. So A, B, C, D, I'm going to keep them all. And I'm going to keep AD, I'm going to keep AC, I'm going to keep CD, CE. Okay, so I'm going to arbitrary, I'm going to cut it off right there, and we'll see what it looks like. Now what happens is, as we remove terms from the and incorporate their effects into the noise, we'll be able to see a little bit more deeper. So the p-value will change, and the coefficients will change just slightly. Let's hit it. And there we go. So we are getting some borderline stuff. You know, at this point, I like to maybe go to 0.05 again in here. And what I'm going to do is I'm going to, in my model, I'm going to keep D, C, and AD for starters. So to say that these three are the key things that I need to keep in my model. Okay? So if I, again, if I look at the p-values, you'll see where the p-values are now. They're actually going to get p-values. See, there you go. Here are the ones that are just under 1, but here are the ones that are really significant. Obviously, let me go back to my highlighter here. Oops, erase all of this. Here are the ones that are really significant. This guy right here. This guy right here, this guy right here, this guy right here, this guy right here. So those are the things I'm going to keep. Okay? That was my first one. Here's the one I've got. Oops. Let me just close down all the graphs because I got so many of them. I hit the redo button again. There we go. D, C, and AD. So those are the ones I'm going to keep. Okay, so now come up into here. Keep D, C, and AD. Now this is, I'm trying to make an instructive problem here. So I'm going to click OK. And it says, if I include AD, I have to include A. So that's just one of the tricks of the trade, is that if you're going to include one of the what are called main effects, A, B, C, D, E are the main effects, and then the higher order things are interactions. If you include an interaction, you have to have all of its constituent main effects in the model. I didn't make that up. It's just the way that it is. So I have to put in app type, click OK. Click OK. There's my Pareto. Interesting that now it doesn't come out as significant. So maybe I do want to just remove that. In fact, I will. Let me leave it in just because we'll build the model and I'll take it out at the very end. Okay. I'll show you what it looks like. It'll maybe be instructive to look at the model. Okay. So now let's take a look at the model. And here now I've got a model that I'm going to read off to you. It's going to be y is equal to 73, I'm going to abbreviate a little bit, 0.15, plus 2.375 times A. You see it's not a very big thing there, plus 8.487 times C, plus 16.2 times D, plus a negative 3.162 times AD. Okay. Now, if this interaction were bigger, every time we had to add D or A, we'd have to really be seriously thinking about it. We'll come across an example at the end of this where that happens. But for now, seeing that when we removed all that other stuff, now this looks like it's the noise and this looks like it's noise, we're going to get rid of this and this too in our model. That's just a Control E again. You can see that the analysis is iterative, but it's very observational. We're really just looking at graphs, which is good. Get rid of AD, get rid of app type, hit the OK button. And there we go. Very simple model now. It's going to be a little bit different than it was before. Just to show you. Oops. Didn't scroll up. I'll scroll up now. Okay. Now our new model, this year's model, is constant is y equals 73.15. That doesn't change. Plus 8.487. That changed slightly. C times C plus 16.187 times D. That's pretty easy. So we can actually predict now our percent. Remember, y is percent complete, based on those different things. So what's really interesting is that, I think, is that we tested out these solutions of give an example, give a long description or short description, and so forth. Let's actually see what that looks like if we go back to our, let's go back to our whiteboard. Here was our whiteboard, remember, and what we found out was that in this case that it was, we got D was a, what was it? C was like 8.2% lift, and whether we provided an enhanced example, that was like a 16 point, I can't remember, let's say 2, lift on that. So the idea is if we use the enhanced one, we get an additional 8%. If we use the enhanced example, we get an additional 16%. Didn't matter versus region. Didn't really matter which app type. Whether we provided a negative example didn't matter either. So think about that. That's the difference. And we're proving that by putting this stuff in, doesn't matter by region, doesn't matter by application, that if we enhance the description, we get an additional 8% lift. If we add the example, we get an additional 16% lift. Pretty cool. Tried out a lot of things, evaluated them for noise. So I know that was a long example, but hopefully it gave you a good flavor of what's out there. And now I think we'll be able to run through the rest of this pretty quickly. However, I do want to recap the example. And so just to say what the process was, DOE process, and it was this. Number one, we decided upon factors. That was the A, B, C, D. You know what, I'm going to put in a step 0 here. Okay, step 0. Step 0. We decide upon the response, the output. That's the Y, the output, whatever. Okay? That was the percent complete in the example here. We decide upon the factors. These were the A, B, C, D, E's, right? And we also decided upon their levels. That was the lone versus least, the -1s versus +1, Midwest versus North, Northeast, etc. Okay? Then we decided upon, I'm going to break this up just a little bit, because really, we really didn't start out by looking at the A and the B factors. What we really did was we looked at these guys right here, and we're going to call these control factors. Remember, this was example or description, example, negative example. Those are things that were within our control. Those were control factors and levels. Okay. Then we talked about noise factors. These are things that help us understand how to control noise better. That was A and B and their levels. Then we ran the experiment. Decided number of runs. Remember we said 16, not 32. Why not 32? Well, because we thought we could save some money by running 16. Okay, I'll show you what our thinking is going to be as we go through a little bit later. Okay, and then we ran it. Ran it. Got our data for Y. And then we analyzed it. Finally, we didn't do this, but we thought about it and we talked about it. We could optimize, right? That means, in this case, it was implement the solutions, right? To say, well, E doesn't make sense. E didn't work, but C and D sure did, and we can implement those. Okay, so that's the recap on the example. So now let's go through actually, I think you will understand the class examples or the examples that are found in the text much more easily, and we can move pretty quickly. So just to quickly talk through this, now that we're kind of in slideshow mode, we want to talk through what is DOE, why to use it, some terminology, and then we'll talk through factorial experiments. Just really do two more examples, one full and one fractional. Okay? All right, as talked about before, DOE is really a systematic, cost-efficient way to develop an understanding of your product or process and use it to make improvements. We talked about that, but think of it as you're changing the inputs. You're actively changing the inputs to see what happens. Now, there's lots of different types. As I said, we're going to do 2 to the K. Why would you do it? Well, 3 different reasons. One is to establish cause and effect. Sometimes we have 2 things that are related to each other, but one doesn't affect the other. We can't make improvements based on that. We can make predictions, but we can't make improvements based on that correlation that is not causal. However, with DOE, we're actually wiggling the inputs so we can see if the outputs wiggle or if they don't. Second thing is we can find key interactions. Now, that might be the difference between running a process in a common sense fashion. Oh, let's just do what we think is right. Let's just use people's ideas that are coming to them off the cuff. Or really understanding deeply what's happening. As I change one factor, the influence of another factor is now changing. That's called an interaction. Third reason is that it's economical. Think about having to run all of those solutions in a one-at-a-time, trial-by-trial method. That would take a long time. It's expensive in time, and it's also expensive in cost, and you can't check the interactions. And finally, to build a mathematical model, I've been trying to convince you that mathematical models can be very powerful, not just because we understand the story of sort of, does training help people in the call center, but we actually can quantify by how much. Okay? Gone through this example before. Cause and effect often holds lurking variables. Ice cream sales certainly don't have anything to do with drowning deaths, but they are correlated with them. So what does that mean? Well, it means that there's some other variable, maybe the temperature, or maybe the number of ice cream vendors, or maybe the number of people on a crowded beach, that's correlated with both of these things that's driving this. Okay. In this case, it's obvious, but in many cases, it's not. And it still happens to be true that there's correlation between things, but not causation. Okay. Very quickly, terminology, and we've already talked about this. Our output in DOE is often called a response. Our inputs are called factors, and the settings that we put them on are sometimes called treatments, but they're most often called levels. The things that are being measured are called experimental units. All right, so let's go through an example. In a study to reduce absenteeism, a school was used to look at DOE. A school used DOE to look at how the number of absences was affected by the callback method. Callback method 1 and callback method 2. In this case, the experimental units are students. The response is the number of absences, and the factor is the type of callback method. In fact, the levels are method 1, method 2. Okay? In the example that we did before in financials, the experimental units were in this case, were the people who received the applications. The response was the percentage complete. Some of the factors were, did we include a negative example? Okay, got it. Did we use the current or the enhanced example? Did we use the same or different description? Is it the Midwest or is it the Northeast? Which region? And what type of application is it? Now, factors come in 3 flavors, 3 general flavors: control factors, blocks, and nuisance factors. You can lump blocks and nuisance factors kind of together because basically the control factors have to be in there. You have to have a control factor to run the DOE. Otherwise, what's the point? Otherwise, you're finding out things that are just noise that you really don't have any control over. All right. Blocks and nuisance factors, on the other hand, are things that you add in there because maybe you can't control them. You can't run a controlled experiment, but if you account for the variation that's there, it can help you better see into the variation of the control factors so that you can use the control factors more, so that you can actually see how much the control factors really do affect things. Okay, so for example, total school enrollment might be a nuisance factor. Like there may be more students at one school versus another. So you might want to take into account which school we're looking at. You also might want to do a percentage absence instead of a regular absence. That's another way of getting rid of that nuisance factor. Another nuisance might be, well, we may get more absences in May than in April. So if it ran over those 2 months, you might want to account for which month it was. Now, there's a few different things that we're going to try and do to control noise. The first is the thinking about the laboratory setting. Sometimes for a limited time, certain noise factors can be controlled. I'm not sure you always want to do that in an operations experiment because you want that noise to be in there. You want it to be robust enough to work in a real situation. We already talked about block and nuisance factors. If you can't do either of those, we're going to use something called randomization. Don't worry, Minitab does it automatically. It just says switch the orders of or randomly put the order of the plus ones and minus ones, if you will, in terms of which run appears where. And that helps you spread out and account for things, or handle and keep the experiment valid in case you missed a big factor, in case you missed any factors. Like, for example, there may be something which, let's suppose you were looking at a lawn crew and you were trying to measure their efficiency for a number of different factors that were there. What happens if you put, like, you had one group all drinking water in the morning and not in the afternoon? You might think that it was the water that was helping, or that maybe that the water didn't help. But if the outside were also heating up and you didn't account for that in the model, that might be a problem. So when you randomize things, maybe you wouldn't assign all the people who were drinking water to be in the morning. Maybe some people would also be drinking in the afternoon. Drinking water in the afternoon. I'm careful about that. I don't want to combine drinking and power tools. But drinking water in the afternoon, and that way we'd be able to separate the effects out from temperature and from that water. Anyway, that's just the idea. You randomize the runs in the experiment. In the example that we had where we sent it out to the northeast, northwest, it didn't matter because we're doing it all at once. Okay, let's take a look at the model. We already did see this model before. For some reason we use A's and B's. Who knows why? A response is a Y. Usually, basically, a DOE model is an adjustment from an overall mean. So we'll start with that mean, and then we'll add various, these are the different factors, and their effects are the coefficients or the constants in front of them. So for this example, we have a 2-factor DOE, a very small one, where we have we have 2 main effects, we have 1 interaction effect, and we have 3 coefficients, 1 mean. So to run a full factorial, we would need to estimate 4 things. We would need to estimate, and this is kind of a key to the difference between thinking full factorial and partial factorial and all that kind of stuff. Oops. Okay, the difference is we'll use green here because then maybe we can see it, is that we need to sample 1, 2, 3, 4 coefficients. So a full factorial would need to have 4 runs, 1 run each to estimate each of those. Okay, and notice that we have 2 factors, right? And 2 to the 2 is equal to 4. So 4 is a full factorial. That's how that works. Now the idea here is that if I ended up having a model like this, if you told me what the value of A was and you told me what the value of B was, I could plug it in and tell you what the response would be. Okay? That's the idea. We already talked about this for the single phases. We have these. We already gave you approach. All right, so now let's go into running some factorial experiments. And what I'm going to do is I am going to do the yield experiment. The following example uses the data found in yield sheet on DOE intro.xls. Okay? So this one may not be one. This one is definitely a manufacturing type of situation. Okay, so before we get into the file itself, let's just talk about what the factors are there. So we've got a chemical plant in this case, and they want to improve yield, which is an output or a response. So my output is yield, and they want to, so yield is the output here. This is yield. And they have three factors, which we're just going to call A, B, and C. The temperature that they have the mix at. So if we put in these chemicals, we'll have a temperature. The concentration that a certain chemical is at. And finally, do they add a catalyst, or what type of catalyst do they add into that? A catalyst is just another chemical that helps a chemical reaction happen a little more easily. So these are the three. And let's just kind of walk through how they would do that. So the first thing is, let's suppose that they had already brainstormed and already come up with their ideas, and that these were three factors that they really wanted to run this on. Okay, and that was a reasonable thing to do. So the first thing is, we need to set the factor levels. So the idea is we're going to pick two somewhat extreme but existing variables for each factor. Let me draw out what that would mean. So for example, suppose that the temperature that you put into the chemicals that you heated the cauldron up to, right? You have some cauldron making some witch's brew or something like that, and let's say the temperatures that you typically had that cauldron at were somewhere between, they could be anywhere from like 120 on the really high side, super high side, maybe 200. Well, what you want to do is maybe pick some pretty high, but not super high. You want them to be extreme, but not super duper extreme. So maybe 160 to 180. And maybe I haven't drawn this well to scale, but I think you get the point. You wouldn't want to pick two different things. You wouldn't want to pick. You wouldn't want to pick, something that was so extreme that you'd never seen it before. Nor would you want to pick two things that were too close together. Okay, so you definitely wouldn't want to pick, say, 171 and 169 in this thing. Okay, just some tips on choosing that. Okay, concentration would go between 20 and 40%. And the catalyst, suppose there were 5 different catalyst types. Notice we've got numerical and categorical types. A catalyst is a category. The other two are numerical. Catalyst, we might want to consider what would be the worst and the best catalyst. So we picked the worst and the best, or what we thought would be the worst and the best. Okay? And then we coded them as follows. So we took A, B, and C, went from low to high, and we used logic where we could. So, for example, it wouldn't make sense to use the 180 as the high temperature. We could do it and put that as low. We could, but it wouldn't make sense. That would confuse people. So instead, we're going to put the low here and the high here. Concentration like this, catalyst like this. And we're going to code them as -1s and +1s. Okay? Keep that in mind. Now, we didn't do that the last time. Last time, we just entered them in as 160, whatever. When we actually have Minitab do it, which I'm going to show you how it happens, Minitab will automatically create these -1s and +1s, and it'll help you. I think it'll help you think about it. Okay, so if we ran a 2 to the 8th, that would be a full, as we just said, right? Because 2 to the 3 is equal to 2 times 2 times 2, and that's equal to 8. That's all the different combinations of temperature, concentration, and catalyst. If we had the budget to do it, why not? Okay? So the next thing is to put it together in a variable table like this. So Minitab will do this for you. You'll notice that there's a pattern here. -1 +1, -1 +1, -1 +1, -1 +1, minus, minus, plus, plus, minus, minus, plus, plus, minus, 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 plus, 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 plus. Minitab would start with that, and you'll notice that covers all the different combinations. and then essentially it randomizes. Minitab will randomize. So for example, you will find this particular run, let me use my pen here, you will find this run somewhere, use red, somewhere here. Where is it? Minus, minus, minus. There it is right there. It says do that on the 7th time you repeat this experiment. Now, why would you do it? Well, who knows? Maybe the cauldron has some, or the plant has some characteristics of heating up during the day. So we randomize the run order, and there we go. Minitab, like I said, will do this for you. And then we'll go ahead and we'll prepare people who are going to run the experiment, and then in special forms of instruction, and then we'll run the experiment and get our response. Okay, now just a note here, running the randomized test, if you're going to let people do it, that's something that's often violated, so you might want to watch that. And in our example, we got this. Now I'm going to skip over, there's some things that are done by hand. I'm going to skip over those because if we have Minitab, why not? Okay, why not let it work for us? But as you'll see, there's a number of different ways that we analyze this, and it's just very straightforward. So for example, the mean is just an average of all of these amounts. The effect of A is to take all the plus A's, right? All the A's when A is plus 1, which I will actually highlight here just so that you'll see it. That's a plus 1. That's a plus 1. That's a plus 1. There should be one more. That's a plus 1. And those all go up there. So 83, 72, 68, and 80 divided by 4. That's the plus. And then we'll take all the minuses, 54, 45, 52, 60, and we'll subtract those and we'll look at the overall effect. That's how we estimate the effect of A. All the pluses minus all the minuses, that's the A effect. Okay? That's how it's done. That's what Minitab's doing as well. At this point, and all the rest of the things work exactly the same way, and you can see how they work on the subsequent pages, including the interactions we do on for you as well. To do that, we come up with a huge equation, right? This is only 3 variables, and by looking at these coefficients and which ones are the big ones and which ones are the small ones, essentially we're going to say which ones are going to be crossed out of the model and not. And we can actually look at this right here, and we can say, for example, this is a big factor, this is a big factor, this is pretty big, and all the rest are like pretty small. That's pretty small, that's pretty small, that's very small, that's pretty small. So let's see, ABC would go out, BC is going to go out, okay, oops, did I mark out AC? AC is going to be kept, darn it, screwed up, sorry about that, folks. BC is going to go out, AC looks like it's going to stay in, AB looks pretty small, C looks pretty small. Yeah, we're going to have to keep that because we've got AC, you see. B looks pretty big, and A looks pretty big, and of course we keep the constant. So we get rid of some of those terms, and the model starts to make a little bit more sense, and it's going to be easy. So we're going to see that Minitab's going to do that for us. So let's take a look at how it would look in Minitab. I'm going to do this for you. And although the examples are given on in the book, you know what? I'm just going to walk through. We start out with analyze factorial design, DOE factorial, analyze factorial design. We have to report the data in. We have to code the factors. This time we're just going to leave them as -1s and +1s. And then we're going to do the residual, or the alpha, right, when we do the response. Do alpha. I like putting in 0.1. And there it is. It shows that A and AC are significant. Everything else is not. So that's going to force us to look at, I look at all the main responses and the interaction that's significant. Okay, there's our model, and we can see that A, B, and AC are significant. Now notice I kept all the main effects when I redid it. And that's it. So here comes our model then. and we can use it, and you'll see it's exactly what we had before. And then we'll consider what gives us the best yield for this. So if we look at this and we say what gives us the best yield, it would be when A is positive, B is negative. High yield is good, right? So if B is at the negative, that makes this minus 2.5 plus, right? And then let's see, how about C? C is positive, that'll make that plus, and positive, positive also means a positive there. So we're going to maximize it when A is equal to plus 1, B is equal to minus 1, C is equal to plus 1. And that gives us an 84% yield. What does that mean? Well, that means at the temperature that's the high temperature, 180, the concentration that's the low concentration, 20%, and the best catalyst will give us an basically 83% yield on that. Okay, so that's it. That's how it all works. And let's just do it very quickly in Minitab, just to show you how you can do it pretty quickly. This example happens to be in DOE Intro, and it's on the yield sheet. I'm going to copy it, put it into Excel, into Minitab, which I just closed. Here's my factors. Low, high. Here's my response. Put my graph. Pareto is 0.1. Click okie dokie. Okay, I see A and I see AC. So my next thing is to keep all the main effects, A, B, C, and I'm going to keep AC. And now I look at the significance, and I got A, AC, and B to be significant. So watch what happens. I know you should get used to this now by this point, but what would happen if I tried to take out C? It says no, you have to select C because it's in AC. If you want to keep AC, you have to keep C. Okay, there we go. And that's our model right there. Oops. Right there is our model. 64 plus 11.5 minus 2.5b plus 0.75c plus 5 times AC. That's it. That's our model. And we can plug into that if we want. All right. So now let's talk about fractional factorials. And a fractional factorial is simply something that really helps you, because what would happen in the last example, we had 3 factors, but what would happen if we had 7? Well, if we had 7, you might say, wait a second, this isn't helping me. I don't have the budget to run 128 experiments. So how do we do this? Well, what we're going to do basically is we're going to use something called sparsity effects and also something called the heredity principle, which is talked about in the next section. We'll talk about it tomorrow. Actually, I'll give you an example today, and it'll work and it'll make sense to you. The analysis would help you. But essentially, here's what it works. Here's the way it works. If we had a full factorial, let's say we had 4 effects, right? We could clearly do a lot more than this, but just let's keep 4 to be easy. We certainly could have more than that. Our processes are very complex, so we could have more. And let's suppose those 4 effects were A, B, C, and D. We're going to call those the main effects, or think of those as 1. Okay? Then we're going to call these the next interaction sets, which are AB, AC, BC, BD, and etc. We'll think of those as 2, right? There's 2 factors that come into this. They're called, in fact, 2-factor interactions. Now, what intuitively is, in our brains, is hard to do is go to many factor interactions. Yes, it's easy to maybe see that region could be interacting with my example or my description, but what about the negative example and region and description, or the region and negative example and positive and regular example and description and one other thing? My gosh, that's super complicated. So it's going to be an easier model if we only include the main effects and the two-factor interactions. But it also turns out that by something called sparsity effects, and this comes from George Box, who's a big wig, and yes, in the Box-Cox transformation, he is the box. And that's one of the reasons why I draw the box. Actually, he's a cantankerous old man, but great statistician. Anyway, he noticed, and then there's a theoretical basis for this as well, that higher order interactive effects tend to be less important in the model, tend to be more noisy, more noise-based than lower order interactions and main effects. So if you have, say, in this case, our four-factor interaction, we'd also have A, B, C, D, right? That this would be less important than this, and this would be less important than this, and the two-factor interactions would be less important than the main effects. So we're going to use this to our advantage, and we're going to say, well, if we don't have the budget, let's not try to estimate all these higher order interactions. Let's just get the lower order interactions and the main effects. That's what a fractional factorial does, and that's how it helps us. Let me show you how it works. Now, one of the things that kind of stinks is that there's something called confounding, and confounding simply means that when we cut we don't cut corners, but when we cut out our ability to estimate some of the higher order interactions, what we want to do is we want to essentially, what we do is we lose the ability to determine whether it's actually a main effect or a higher order interaction. It could be either, and so we're going to assume it's the main effect rather than saying it's the three-factor interaction or something like that. And that's called confounding. And Minitab, luckily, is going to help us out understanding what confounding is by telling us something called the resolution. The resolution. So let me go through exactly what confounding is. Suppose we had three factors, okay, A, B, and C. Now, suppose we didn't have the budget to run 8, which would be very small. We ran an experiment with 4 runs. I'm not saying this is a great experiment, but let's say it was this. Now, suppose we wanted to estimate an interaction. Let's say let's say the BC interaction. Let's see what happens with confounding. Well, confounding, it works like this. If we wanted to construct the BC interaction, that would be B times C, right? So negative times negative is negative. A plus times negative is negative. Minus times plus is minus. Plus times plus is plus. Minus minus is plus. But we'll notice now that this column is the same as column A. So if we were going to estimate the effect of BC, it's exactly the same as A. We can't tell the difference. So that would not be such a good experiment because we wouldn't be able to separate the effects of A from another fairly important one, the BC interaction. That's what confounding is. So enter something called resolution, and resolution simply gives you the worst case scenario for confounding. So there's lots of different resolutions, and we'll do an example in Minitab and it'll show you this, but there's a res 3, and don't ask me why they use Roman numerals, but they do. Res 3 is what's called a screening design, and in this case the main effects in a res 3 are confounded with the two-factor interactions. Not super desirable, but I might want to use it in a screening experiment. So I have lots of different variables. I want to just screen out one of the important main effects. I might be able to do that with a res 3 design. Res 3s can handle lots of factors, but they can't tell the difference between main and two-factor interactions sometimes, so it can't be that great. Then there's a Res 4 design, and I don't know why I missed the indent, but there's a Res 4 design. And these are either 1, think 1 plus 2 equals 3 for Res 3. For Res 4, 1 plus 3 is equal to 4, or 2 plus 2 is equal to 4. So the two factors are confounded with other two factors. Not so great, but this is pretty good. The ones are confounded with the three-factor interactions. In this case, we're going to assume that it's not the threes, but it's the ones that make the difference. So Res 4s are pretty good. Res 5s are really good. So 1 plus 4 is equal to 5, or 2 plus 3 is equal to 5. In this case, our main effects are confounded with four-factor interactions. No big deal there. And our two-factor interactions are confounded with threes. Not so bad either. So in this case, we're going to go with the ones and the twos. So Res 5s, good designs. Try to at least get a Res 4 if you can. And if you're going above, use this sort of rule of thumb, okay, as we're doing this. So a Res, this is maybe a rule of thumb, and we'll break our thumbs. No, we'll break this rule a little bit in the next section. But a Res 3, try and get a Res 4. Oops, I don't know how to write Roman numerals. You know, that's the first time I wish I would have studied that in grade school. Just kidding. Res 4 or Res 5. Okay, design. Try for this or this. If you're going above, if you're going to say Res 6, and yes, they exist, or Res 7 or whatever, you're probably wasting money. You're probably wasting cash. And if you're doing Res 3 or not, you're probably wasting cash by running an experiment that's not going to give you what you want. Okay, so try and run a Res 4 if you can. Let's just and here's a table that you'll see a mini tab as well, and this tells you the number of factors and the number of runs, and it'll say whether it's a Res 3 or 4 or whatever. So let's do an example. So for let's do 6 factors. So if we had 6 factors, if we decided to do an 8-run experiment, we would have a Res 3 design. If we did a 16-run experiment, we would have a Res 4. And if we did a 32-run experiment, we'd have a Res 6. I would be inclined to probably run that Res 4. Okay? Why? Because, well, 32 is not bad. If I can afford a 32, I might be able to do it. But Res 6 is probably more than what I really need. So Res 4 is maybe a little bit less. So it sort of depends on how many interactions I have that I think might be significant. That would kind of guide that. But I would tend to be inclined to run that Res 4. Minitab also has this picture. Okay. And how do you do the analyzing? The same way that we did it before. That's the beauty, is that they're analyzed exactly the same way. All right, let's go through and do an example. I think all this stuff is easier to understand in the example. I'm going to go ahead and do the example that's given on slide 64 in your book, which uses the advertising DOE, on advertising DOE, and it's given in, you're going to get it for homework, so may as well, right? So in this case, we have a marketing department. They ran a designed experiment to test the effectiveness of their ads, and for each of 16 trials, they tracked the sales related to each ad config. Factors they considered were color, placement of the ad, whether there was a free offer, what day it was posted, and the font. Okay, so let's start out by talking about how they decided upon. Let's take a look at the data first. It's always helpful. I'm just going to open it up in Excel first. And let's give it an advertising DOE. Here it is right here. So they had various things. They'd have to decide on the levels. That would be the first thing that they would do. In this case, they looked at sales and $100,000 from this particular ad campaign. And they'd set up the -1s and +1s. For example, it looks like all of these are control factors, except for maybe day. But even then, what day did it go into the ad? No, I'd say it's probably a control factor. Placement of the ad, they might consider center of the page versus one of the edges. That might be a extreme way of looking at it. Free offer, yes or no. What day of the week did it come out? Did it come? Maybe it was a weekend versus weekday, or maybe it was Monday versus Saturday. Those might be the thoughts. And fonts might be large font versus small font, or whatever. There's a number of different things that you could do. If you're looking at styles as well, font styles, that could be another factor that was added in. Here we've got 5 factors, okay, and 16 runs in the experiment. Okay, now how do we decide on the 16 runs of the experiment? Let's just get this into Minitab for just a moment. Now, if we were starting from scratch and we didn't actually have the data yet, what we do is we go to Stat, DOE, Factorial, Create Factorial Design, come into Minitab, and it says Number of Factors. So here we choose 5 because we have 5 factors. And if we can look at Displayed Available Designs, this helps us think it through. This is actually fairly simple. We have 5 factors. If we ran a 8, we'd only have a resolution 3. Not so good. Well, if we run 16, we've got a res 5. Sounds good to me. Res 5 is kind of the sweet spot. So let's go ahead and run that. That kind of answers the first question. What is it? What resolution? There it is. We're going to choose the 16 run, which it says is a half fraction. Full would be 32. And click Okie dokie. And Minitab will actually do it for you and set up the ones and zeros. At this point, you could have gotten the sales response, right? You go out and you actually get the data. But we've already got that. So I'm going to analyze what we had in here. And now I've changed these to A, B, C, D, or whatever. Okay, or font, and so forth. I want you to see, basically, in the last case, when we did this resolution, remember, we ran a resolution 5. We created this resolution 5 design. Here it is right here, and it says, no kidding, the ones are with 4s. You see that? It says we can't tell the difference between A and the B, C, D, E interaction. Big deal. I'll just say it's A. Here's another one. We can't tell the difference between A, B, and the C, D, E interaction. There you go. Same sort of thing. 2 plus 3 is equal to res 5. Okay, let's go ahead and do this for this guy now. Factorial, analyze factorial design, and we're going to put our factors right here. Oops, I have to set low and high. This time it is minus 1s, plus 1s. My response, look at the graph, put the point 1 and B. Just look at the Pareto this time. And there you have it. It's B, C, the BC, and D. Okay, so let's go through, and first thing would be I'm going to get rid of all these except the main effects and the significant interaction. It's not the only way to analyze this, but I think it's a reasonably straightforward way of doing it. Click OK. Now we got our p-values, and there it is. There's my model, B, C, D, B, C, B, C, and the D. Now, if you want to be less aggressive at this point, and you want to look at the 0.05, that's fine with me. It's okay with me. Again, I like to be a little bit more aggressive. In this case, both roads lead to Rome. BC, the BC interaction, and D. So now we're going to remove A. Color doesn't matter. Font doesn't matter. But placement, free offer, and day of the week that we send it out do. And this is how much they matter. Placement matters the most. Whether there's a free offer matters. And then there's interaction between those two things. That's interesting, right? So there's an interaction between whether we give a free offer and where we place it on the page. Let's take a look at what that interaction means. There's a good way of looking at that, and if we go to Stat DOE, Factorial plots, we can do main effects plots, which aren't that interesting, actually. Let's just take a look at this. They're not going to tell you anything we don't already know. Oh yeah, I have to select a response. Here's the first thing. Here's the main effects plot. This just tells me that placement and free offer are big compared to everything else. We already knew that. But the interaction plot is actually kind of interesting. I'm going to look at sales again. In this case, we wanted to look at placement, pre-offer. And I'm going to look at day as well because it came out not significant. So you can see in this case where they're sort of parallel, like right here, this is placement and day. No significant interaction. The same effect of going from -1 to +1 on day, on placement, right? Here's day, -1 to +1. It's the same for the +1 placement or the -1 placement. But if we look at free offer, when we go to -1 to +1, the effect is much more powerful. Free offer works better if we have the placement at +1. Maybe that's in the center of the page versus on the edge. So if that were true, the free offer would work best there. Now sometimes you'll get kind of crosses like this, which would tend to show that they interact negatively. These two, there's a synergistic effect, right? Because the separation is actually greater here than it is here, but it's the same direction. If you got crosses, then it would be the opposite. Okay. So, so that's that. So if we're going to look at our model, let's take a look at our model. One last thing here. Let's take a look at our model, and it says that our model is y is equal to 20.275 plus 3.6 times placement plus 2.9 times free offer plus 0.725 times day plus 1.375 times placement times free offer. Right? Okay. So if we were going to plug into our model, as is given kind of on this guy right here, we're going to plug into our model. Whoops. Just like this. Come on, show me. No, didn't like that. I thought we were going to plug in. If we were going to plug into our model, color, well, color's not even in there, so this goes out. Placement of the ad, that gets a 1. Free offer gets a -1. Day posted and font was E, that goes out. We only care about these guys, and we plug these 1, -1, and -1 into our model, which would trying to see where it was again. I need to go to Minitab, I think. There we go. No, I don't know why. I guess I must have gotten rid of it. So, you know, placement is a 1, free offer is a -1, day is a -1. You can plug that in and get our answer. Okay. So this was a fairly long lecture, and I hope you enjoyed it. Basically, we covered 2 things. One is recognize when DOE might be helpful, and the second is we talked about how to create, execute, and analyze factorial DOEs and build models from them. I hope you found it illuminating and helpful, and we'll catch you at the next lecture, where we'll be talking about examples and structure, and we'll review the framework, give you more examples, and then we'll cover Schuhart control charts. So thanks a lot. Talk to you soon, and we'll see you again.